Hello everyone, and in this video, we're going to be taking a look at a problem from the 2023 IMO. And this time, we have a number theory problem, unlike the rest of the videos on my channel. So without further ado, here it is. We want to find out all positive integers n is greater than 0, such that when we have the divisors d1, d2, all the way to suppose dm of n, and these are all increasing order, so d1 is less than d2, d2 is less than d3, and etc. Such that we must have d1 divides d2 plus d3, d2 divides d3 plus d4, and so on, up to dm minus 2 divides dm minus 1 plus dm. In other words, any term in the sequence must divide the sum of the two divisors that come right after it in this sequence here. So how will we get started on this problem? Let's try looking at some small cases to get a good understanding of what's going on. So let's test out the values 1 through 16, suppose. And then here's 13, 14, 15, and 16. So let's see which ones work. For 1, obviously it works, and 2, obviously it works, and 3, obviously it works, because they have less than 3 prime divisors. And in general, all primes work. And then 11 works, 13 works, and that's all the primes on this list. 4, the divisors are 1, 2, and 4, and 1 indeed divides 2 plus 4, so that works. And in general, any number with 3 divisors works as well, because we only have to consider the number 1. 9 is 3 squared, so it has 3 divisors, and that's the only other one with 3 divisors. For 6, we have the divisors are 1, 2, 3, and 6. Even though 1 divides 2 plus 3, 2 does not divide 3 plus 6 is 9. So that does not work. For 8, we have 1, 2, 4, and 8. And 1 divides 2 plus 4, and 2 divides 4 plus 8. So that works. And for 10, we have 1, 2, 5, and 10. And 2 plus 5 does not divide 10. So that doesn't work. 12, we have 1, 2, 3, 4, and 6, and 12. And 2 does not divide 3 plus 4. 14, we have 1, 2, 7, 14. And 2 plus 7 does not divide 14. 15, we have 1, 3, 5, 15. And 3 plus 5 does not divide 15. And for 16, however, we have 1, 2, 4, 8, 16. 1 divides 2 plus 4, 2 divides 4 plus 8, and 4 divides 8 plus 16. So that works. Now let's try taking a look at what happened with these wrong ones here. We might want to list the prime factorization of these numbers, because they seem to relate a lot to the divisors. So we have 1, 2, 3, 2 squared, 5, 2 times 3, that's 7, 2 cubed, 3 squared, 2 times 5, 11, 2 squared times 3, 13, 2 times 7, 3 times 5, and then 2 to the 4. And I'm going to circle the ones that didn't work. And then here's the other one and the last one. So the ones that didn't work are 2 times 3, 2 times 5, 2 squared, and this one also didn't work. 2 squared times 3, 2 times 7, and 2 and 3 times 5. And the ones that did work are all the uncircled ones. Now what we might notice is that all of these numbers have more than one distinct prime divisor, and all of the uncircled ones have only one prime divisor. So that's the main conjecture that we want to prove. So conjecture is that n is equal to p to the power of k, where k is greater than or equal to 0, because 1 also works, and p is prime. This is what we want to prove. How can we get started on proving this? We might want to start by considering some other cases, like we might want to try looking backwards. So n p minus 1 and n over. If there were two distinct primes in there, then we might want to start working with n over p2, for instance. Then we need that n over p2 divides n over p1 plus n. And that means that n over p1 plus n over p2, which is equal to p2 over p1 plus p2 after simplification, is an integer. And this means that p2 over p1 is an integer, so that means that p1 divides p2. But since they are both primes, that means that they're equal, which contradicts the fact that they're distinct. So hence this cannot happen. So it must be something like n over p minus 1. The next term must only contain p minus 1, so that's n over p1 squared. And now we want to know what happens whenever there's another thing like n over p. There's another prime p2. And what happens if p2 is less than p1? Well, that would mean that it comes first right over here, and that can't happen. So that means that p1 is less than p2. So hence the next one here, we want to see what happens if it is n over p1 p2. Then we'd have n over p1 p2 divides n over p1 squared plus n over p1. And that would mean that n over p1 squared plus n over p1 over n over p1 p2, which is equal to p2 over p1 plus p2 is an integer. Notice this? It's right here, and that implies that p2 equals p1, which can't happen. So this case here can't happen. So the next one must be, so it's n over p1, n over p1 squared, and now we know what n over p1 cubed. And now what would happen if p1 is greater than p2 squared? Then that would mean that there would be something over here, and that can't happen, because we know that these are the largest primes. So we must have that this next one here is the form n over p1 squared p2. And then we have n over p1 squared p2 divides n over p1 cubed plus n over p1 squared. And that implies that n over p1 cubed plus n over p1 squared over n over p1 squared times p2, which ends up equaling p2 over p1 plus p2 is an integer. And this is just the exact same thing, so p1 equals p2. And hence we have n over p minus p1, n over p1 squared, n over p1 cubed, and now n over p1 to the 4. You might guess what's going to happen next, and it's assuming that this next one is n over p1 cubed times p2, and this again yields that p2 equals p1. So it ends up being this should be p1 to the power of 5. And then what do we do next? Well, you guessed it. We're going to do p1 to the 4th times p2. And we end up getting p2 equals p1 by similar logic, so p1 to the 6th. And we just continue this process all the way down to the number 1. And that's equal to n over p to the power of k for some k. And that means that n equals p to the t1 to the power of k, where p is prime. And here we're assuming that k is a positive integer because we're assuming that n has a prime divisor. But if k is equal to 0, then it also works fine because that gives a case n equals 1. Therefore, the answer is just p1 to the power of k, where p1 is prime and k is greater than or equal to 0. The main tactic that we used to solve this problem was looking at some small cases over here. We looked at some small cases to see what the general pattern was, and we ended up conjecturing that this was the case. And we ended up working backwards, starting with the largest and going all the way back to the smallest in order to prove this. So thank you so much for watching. I hope you enjoyed.